Hello all. In this video we will discuss a very useful tool in ETABS, and that is called the Section Designer. This tool is used for the analysis of cross sections, to calculate the cross-sectional properties, to determine the moment-curvature relationship for a cross section, and also to calculate the axial-flexural capacity for a cross section. So before going to ETABS, let's have a quick overview of this tool and also the theoretical background and numerical procedure which is implemented in ETABS for this useful tool. So in a real structure, you can have several complex kind of cross sections which are based on different materials, and the geometry also can be complex. For example, you can have built up cross sections, composite cross sections, and you can have cross sections which are composite filled cross sections. For example, this one which is having a steel tube which is filled with concrete, and then again it has a steel cross section in it with some rebars also. So it's a very complex cross section, and ETABS will not provide a template for defining such kind of a cross section. So you also can have these filled box cross sections, encased I section here in concrete. You can have steel cold form cross sections, hot rolled steel cross sections. You can have several shapes of precast cross sections and also cast in place cross sections. So for most of these kinds of complex cross sections, there is no template available to define their shape and their materials. So this useful tool, the Section Designer, basically provides you the facility or the convenience to model any kind of cross-sectional shape made of any kind of material. So it gives you that flexibility to define your own complex cross-section in a very simple manner. Similarly, you can also have several standard cross-sections which you want to define maybe yourself. Maybe they are all made of same material, but their shape is maybe such that the template is not available. So in those cases also you would like to use these Section Designer. So you can have, for example, these kind of cross sections, these shapes for example, and also you can have several kind of steel cross sections which can have different kind of these shapes. So all of these cross sections, they will be defined using Section Designer because their template or defining their cross-sectional shape is not by default available in ETABS. So you can find this useful tool here when you define the cross-sectional properties for frames. So here you can have this section shape, and in this list you will be given a list of several cross-sectional shapes, the templates which are already available. But if your cross-section is not available in these templates and you want to use Section Designer, so instead of going for this option, you will select this thing which is the Section Designer here while defining your cross sections. So in a moment we will go to ETABS and I will show you how you can use this very useful tool. So this is how the Section Designer looks like. You have a canvas, this is the canvas, and you have some drawing tools available, some selection tools available. You also have these snapping tools for your cursor available, and here you can use this menu to draw also. You can use these options also to draw different kind of shapes on these canvas. And the three primary outputs which this Section Designer is going to provide you are these. This one is for section properties. Section properties we will see in a moment. This one is going to give you the axial-flexural capacity surface, axial-flexural capacity for that cross section. And this third option is going to give you the moment-curvature relationship for your cross section. So moment-curvature relationship. So here these section properties, this first option, this one is shown here. So you can see here that there are three orientations of the two axes for these properties. Two axis is this one, and it is by default coinciding with the y axis. So 3 axis is coinciding with the x axis. So you have two local coordinates for defining your cross section, and those are 2 and 3 coordinates. So you can have these cross sectional properties at default, which means this 2 and 3 which are coinciding with x and y directions, and for the principal axis of the cross section, and for any user defined axis. So the cross-sectional properties can be reported for these three kinds of orientations. So we will see these options in a moment. Let's see what are some of the properties which ETABS is going to provide you for your cross-section. You can have the center of gravity. You can have the properties which will be used in the analysis purpose, basically for the construction of the global stiffness matrix of the structure, which means the area, the shear areas, the moment of inertia about 2 and 3 axis, and the torsional constant. Similarly, you can have design properties, which means the radius of gyration or the section moduli for different cross sections, and then the plastic modulus. You can also have the principal axis, the moment of inertia about principal axis, and in this case, if your cross section is symmetrical, your principal axis will be matching with the default 2 and 3 axis. That's why the I major and minor here, you can see these two values, they are matching with the I22 and I33 values here. But if your cross section is not symmetrical about any of the axes, then these values will not match. And you can also have the plastic neutral axis location, and also this value is 0, 0, because the cross section here is symmetrical about both of the axes. The area of the cross section and mass is distributed uniformly about both of the axes. So these are some of the cross-sectional properties which the ETABS will be reporting, and when you define a cross-section using Section Designer, these properties will be assigned to that particular cross-section. And you can also click on these properties to check the description here. So for example, if you click on this area, it will give you the description of that particular property. So as I have mentioned in last slide, that one of the outputs which you can get from Section Designer is the moment-curvature relationship. So for any given cross-section, you can get this plot, which is the graph between moment on y-axis and the curvature, cross-sectional curvature on x-axis. So you might already know that if you have this cross-section, for example a rectangular cross-section, and let's say this is the strain profile and this is the neutral axis, so you can divide this extreme fiber strain epsilon with the neutral axis depth to get the cross-sectional curvature. So let's call this as C. So the curvature phi will be epsilon over C. So for all possible moment values which can cause any strain profile, these values, software will calculate this cross-sectional curvature and you will get this curve, which is the moment-curvature relationship. So this relationship will give you a lot of information about your cross-sectional capacity, but most important is the yield capacity, which is this one. This is the My. So it is telling you that this is the moment at which this cross-section will fulfill the failure criteria which is defined in the material of this cross-section. So which means this is the moment capacity of your cross-section. So you can have these kind of curves for any given axial load, because the axial load interacts with moment. So if you increase this number axial load, your moment capacity will reduce. And you can also have these values for different angles of bending plane. So for example, if your bending axis is not coinciding with the principal axis of the cross section, then you can give that angle here and you will get the capacity curve corresponding to that bending angle. So the Section Designer will also give you the point by point coordinates for this curve, so you can copy those points and plot yourself. So this is a very important output from Section Designer. This curve itself provides you a lot of information about the capacity and properties of your cross section. So all the nonlinear material stress strain relationships which you will assign to your cross section material will manifest them into this moment curvature relationship. So this is the primary action deformation relationship at the cross section level. Just like the stress strain curve is the primary action deformation relationship for materials. The other very useful output which this Section Designer is going to give you is the axial flexural capacity of the cross section. It is defined by this capacity surface. So this is a capacity surface, which is a three-dimensional surface or a graph between the axial force P and the moment in both 2 and 3 axis directions. So every point on this surface, every point here for example or here, corresponds to a combination of this axial load and the two moments which will cause the failure in this cross section. So all of these points basically on this capacity surface here, they are corresponding to a particular failure or the failure scenario in the cross section. So that's why it is called the capacity surface. And these P, M2 and M3, basically this is the P axial force in Z direction, and this is the two moments about X and Y directions, for example. These three values are called the stress resultants. So if you, for example, have a column which can have biaxial bending, then the capacity of that column cross section will be defined by this full capacity surface. But if you have, for example, a beam which can only bend in one direction and can have axial force, then its capacity can be defined by just P and M3 curve. So that will be a particular slice of this surface which will be P and M3 relationship. So you can have different views of this capacity surface in the section designer, and you can have any slice of that surface also. You can see it separately. For example, the top view, which means that only M2 M3 relationship and the P will not be shown. And for example, you can have any P M3 relationship or P M2 relationship. All of the cross sections of this capacity surface can be seen with different options available in section designer. So here this is the form where you will see this 3-dimension interaction surface here. So you have P, you have M3 and you have M2, and this surface basically defines the capacity of this cross section. So we will see this form in more detail in few minutes when we go to ETABS. So these are the section properties which the ETABS will report. So you can have these all section properties calculated for your special complex kind of cross section. So now let's quickly review the underlying numerical procedure which is implemented in section designer to calculate all of these outputs which we have seen. The underlying idea for this numerical procedure is called the fiber modeling approach, and this approach says that if you have any general cross section, so for example this is a general cross section which can have any shape, general cross section. So the idea says that you can divide that cross section into small fibers. So it's like you are meshing this cross section in both directions to get very small discretized parts of that cross section, and each part you are calling it as a fiber. So for example, you can mesh this general cross section into this shape, and here you have all of these small boxes which are parts of that cross section, and these are now called as the fibers. Now the idea is that each fiber can be assigned a different stress strain relationship, and it can independently contribute towards the axial flexural capacity of this cross section. So for example, any general fiber, this one for example, it will have a specific area and its stress will be denoted as the sigma I. So this is the ith fiber in this general cross section, and it locates at the distance yi in y-axis and xi in x-axis. So each fiber or part of that cross section will have an area, will have the two coordinates x and y, and will also have the stress strain relationship assigned to that particular fiber. So sigma and epsilon relationship will be assigned for that particular fiber. So these three properties will be given to each fiber independently, and then the whole shape of that complex cross section and the materials which are used in that cross section, all those can be accounted for in this discretized manner. So for example, if you have a general cross section, this one which has maybe opening and which also has maybe the rebars, it can have the pre-stressed strands also, can have the steel cross section embedded also in that, and you can have a material which is, let's say, S1, S2 up to Sn. So any possible complex cross section which you can think of, that can be discretized or subdivided into a mesh, and each element of that mesh will be called as a fiber. A particular material model is attached to each fiber and then solved to compute the response. So for example, for each kind of this boxes or fibers, you can assign a stress strain relationship, and that relationship will be used to compute the axial flexural resultant forces or the cross-sectional response, for example. So basically in this approach, you convert your cross-section from this general shape into the fibers. So the size of fibers basically should be small enough to capture the general shape of that cross-section as well as the exact location of different materials which are available or used in that cross-section. So the fiber model's governing equations will be, in this case, that if you integrate all the stresses in all the fibers with respect to the area, you should get the total axial force. Similarly, if you sum all the moments of stresses over the area, you should get the moments in two directions, mx and my. So for example, if you use the moment arm as yi here, so you should get the moment about x-axis, this one. And if you use the moment arm as the xi, you should get the moment about y-axis. So if you sum the moments of all fibers, you integrate them, you get the total moment. If you sum the forces of all fibers, you will get the total axial force on that cross section. So here you can see that a particular fiber is assigned this stress strain relationship, and that can correspond to steel or concrete or any other thing. So software doesn't recognize concrete or steel or any other material by name. Any material in software is just a stress strain relationship, and that will be used to compute the stresses and then convert it into forces, and then these forces can be summed up to calculate the axial force, total axial force in the cross section. And if you take the moment of those forces about the centroidal axis, you will get the moments in x direction or in y direction. So these are the underlying governing equations for fiber cross sections. We can convert these equations into the summation form if we use the idea of this discretization. So these integrals can be converted into summations like this. So here you can just sum the product of the stress in each fiber and the area of that fiber, and you will get the total axial force. So basically this Fi is same as the sigma I. I should have used the sigma I notation here. Here also this Fi is sigma I, and Fi here is also sigma I. So if you just convert that integral equation into summation equation, you will get this one. So you sum all the forces in all the fibers, and then you will get the Pz. Similarly for Mx, you can take the moments of all the fibers about neutral axis, you will get the Mx. And about My, you can also get the moment for all the fiber forces, and you can get the My. So the moment arm for each fiber will be different now, this one or this one. So if the fiber is here, its x and y will be different. If it is here, the x and y will be different. Similarly, the stress strain relationship assigned for each fiber is also different. So which means the stresses associated with each fiber will also be different. So all these sigma I values will also be different for each fiber. But you sum them all, you will get the moment, the global moment for that whole cross section, and that will be your stress resultant. So this equation basically can handle all possible complex cross sections, but if you also want to include the code prescribed capacity reduction factors, for example shown here as phi1, phi2, phi3, and maybe the gamma factors. So if you want to add those factors also in the equation, because you may want to use these stress resultants for the purpose of design, so the code prescribed factors can also be included in these equations. And if there is any pre-existing axial force or pre-existing moments in two directions, those can also be added to this equation. And now we have these three comprehensive stress resultant equations which can be applied to any general cross section, and those cross sections can have any shape and can have any number of materials. So this is the original governing equation. We can convert them into this form, which is the summation form, and this last set of equations is the most comprehensive form of the same summation equations, including the code prescribed factors or capacity reduction factors. So how we will use these stress resultant equations? We will first define the material models. We will basically define the basic stress strain relationships, these kind of relationships which we have to assign to our cross section. So for example, if a cross section is made of steel and concrete, you should define the nonlinear stress strain relationship for concrete and for steel also first. Then you will assign these stress strain relationships to your fibers in that cross section. The second step is model the geometry of cross section using polygons, shapes and points, and these are called fibers. In Section Designer, basically you define the complete overall geometry of your cross section and the software automatically divides it into different fibers. The third step is to assign the material models or the stress strain relationships to various fibers. The fourth step is that you assume a strain profile of a cross section based on the failure criteria, and that failure criteria will be given in, for example, design codes, or also can be defined in the corresponding stress strain material models. So for example, if you define this material model here for concrete, so you can say that this is the final point, this is the point at which the concrete can be considered completely gone or failed. Same is for steel, and you can also have a particular value for the failure strain of concrete, for example 0.003, and that number basically will come from the building codes. So for a particular failure criteria for a given cross section which you will define, you assume a strain profile, let's say like this, and then you convert that strain profile into stress profile by using the stress strain relationships, so like this. So the use of stress strain relationships, these two curves will be at this stage, converting strain profile into stress profile. So point by point, whatever is the strain value along the depth of that cross section will be converted to stress value using these two stress strain relationships. So once you have these stress profiles already, then you can use the stress resultant equations, because for example, if you can remember, Pz was basically the integration of sigma with respect to the area. So now you have stress profile already, you can just integrate the stress values and get the Pz. Similarly, you can also use the other two stress resultant equations to get Mx and My for a particular fiber. Then if you want to modify these stress resultants using any code specified or material specified capacity reduction factors like phi factor or gamma factor, you can apply that, and then the final values for each material can be obtained. The total stress resultants can be obtained by summing up the values from all the material stress profiles at the end, and then you can repeat the steps 5 to 9 from this one to this 9 for all possible strain profiles based on the prescribed failure criteria of the cross section, and the final computed Pz, Mx and My can be used to plot the capacity surface. So basically you start with one strain profile corresponding to the failure criteria, and then you try all possible strain profiles and repeat this process to get enough points on the capacity surface that you can plot it finally. So you will have a whole set of Pz values, Mx values and My values. So you can plot these values and you can get the capacity surface. So we will see that in a moment. So the application of these general equations can be endless. So you can have any kind of cross section, since the software will discretize it into fibers and each fiber will be given a stress strain relationship. So all you need to know is the stress strain relationship of that particular material. So theoretically software can handle any material or any combination of different shapes or materials. So one very common example of this section designer can be that, for example, when you retrofit a cross section, for example you apply the column jacketing or increase the cross-sectional reinforcement or the cross-sectional size of a cross-section. So you can always analyze that new cross-section in the section designer and compare its result with the previous cross-section. And since now we have very innovative materials for the retrofitting of cross-sections, all we need to know is their stress strain relationships. For example, different kind of fibers are being used to retrofit columns nowadays. So if you have the stress strain relationships for those polymers or those special materials to model them in Section Designer and get the overall sectional response. So with this background, let's go to the Section Designer now and see what are some of the options and capabilities it have. So now I will go to ETABS. Here I have a simple model. I used it from the template from ETABS. So the very first thing I will do is that I will go to this define and material properties, and here I have all the materials which I should use in the cross section. So for example, for concrete material, I have this default 4000 psi, and I can modify that material, and I have all of these elastic properties of that material. In the nonlinear material data, you can have the stress strain relationship for that material or the stress strain model for that material. So here you can see that the stress strain curve definition options are available, and then the default value here is the Mender's concrete model, which you can see here by clicking on the show stress strain plot, and this is the stress strain relationship for this concrete 4000 psi. In tension it has very less capacity, almost 1/10 of the compression capacity. So this compression capacity is shown by this positive stress values. So I will click done, and since in this demonstration we are only using the stress strain relationship of this particular material and we are not going for the performance assessment of the structure, so we will not check all of these other options here. Those will be used in the detailed nonlinear modeling of any particular material. So I will not go for these options. I will just click OK, and I will go for the other material here, which is, let's say, this one, A615 grade 60. I modify it, and you can see that it is a rebar material for steel type, and it has some elastic properties which are the mass density, weight density, elastic modulus, etc. And it also has the nonlinear material data, and if you go for this show stress strain plot, you can see the nonlinear relationship which is assigned to this particular steel material. So I will use these two default materials, and I will show you that how you can analyze your cross section which is made from these two nonlinear materials. So I click OK, OK here, and also OK here. Now I go to define the section properties and then go to frame sections here, and I will click the add new property. I want to add a new cross section, maybe a reinforced concrete cross section, and that should be defined in Section Designer. So I go to add new property, and here I can go for this option, which is the Section Designer, this one. So now we have to define the name of that cross section here. This is, for example, the name of the cross section, the base material, the primary material which this cross section is going to use, and some other properties. But here, more importantly, you can have this Section Designer. So click this Section Designer, and you will start this inbuilt app, which is the Section Designer. So you have this canvas, and you have the drawing tools available, the selection tools, and also the snapping tools for your cursor. So these are the three outputs which are shown here. This is section properties, then the interaction surface, and then the third one is the moment curvature. So let's just define quickly a default kind of reinforced concrete cross section for the purpose of this demonstration. So I go to, let's say, draw and concrete shape, and I go to rectangular shape, this one. So I just click in the middle in the origin, and it by default draw this rectangular cross section, and you can click on this cross section by picking this select object tool, and then click that, right click that basically, to get the basic properties of this rectangular shape. So you can see that the base material, which was 4000 psi, our concrete material, is assigned to this rectangular shape, and the height and width of this shape is 600 mm and 600 mm. So let's make it, for example, the height as 800 mm, this one, and currently it doesn't have any rebars. So I click OK. So now its depth is 800 mm and width is 600 mm. So now let's add some reinforcement in this cross section, and then analyze this cross section. So I go to again draw and rebar shape, and here I have different options. For example, single bar, line bar, rectangle bar and the circle bar. So I select the rectangle bar and I click here. So it by default uses some default dimensions to draw a rectangular shape of rebars. So I have to modify this rebar to set my desired values of rebars and their locations. So I again select this and I right click this to get this detailed form. Here I will customize this rebar values to match my desired values. So most importantly, for example, here is the height and width of this rectangle of rebars. So it is by default 600 mm by 600 mm. So let's say I modify it and I make it, let's say 750. Let's say 25 mm is my clear cover on both sides. So I select the 750 for the depth or height. For width I select, let's say 550. And you can also have the different sizes of bars, and for all of the 4 edges you can select the number of bars. So I will use the default number of bars, sizes and their locations, and I click OK just for the purpose of demonstration. So here you can see that the bars are now set according to my given dimensions. So this is, let's say, my final reinforced concrete cross section, and I want to analyze this cross section. Before I go to these 3 outputs, which are also shown here in this display, let me show you that there are different drawing options for steel sections also. You go to draw and then this steel, and you have all of these shapes which are available. So you can use the combination of these shapes to make your own complex or built-in cross section, and to each shape you can assign a material property. So here for our cross section, if I select this rectangular rebar shape, so I see that the material which is assigned to this rebars is the same one, which is A615 GR60. So we have already seen its stress strain relationship in the materials menu. So I click OK, and if I select the outer box, which is the concrete box, and I right click that box, so here I can see that the material assigned to this shape is 4000 psi, which is the non-linear material for concrete. So now I go to first this section properties. So here I can see that all the cross-sectional properties are shown here. These will be assigned to the cross section which is defined by this section designer. So you can click on each of the property to check its description here. So for this particular cross section, it is a very symmetrical cross section. So the principal axis coincide with the 2 and 3 axis. So if I click on principal axis, essentially I will have the same values. So here you can see the values are not changing because the principal axis are coinciding with the x and y axis, and they are also coinciding with the 2 and 3 local axes of this cross section. However, if you go for this user defined option and you select any orientation of bending axis, for example 45 degrees, and then you can click somewhere and you will see that the values will be changed according to the new axis. So if your primary bending axis is coinciding with the 2 or 3 axis or the x or y axis, then you should go for this default option and not the user defined option. So I cancel this one, and then I go to this moment curvature relationship now, this curve, and here I can see the moment relationship curve. So this curve basically is a non-linear curve now, because the materials which were used in this cross section were given their non-linear stress strain relationships. Those two stress strain relationships manifested their non-linearity in this moment curvature relationship. So this curve will tell you the yield moment, for example, for your cross section, and the ductility of your cross section also. So there are a lot of outputs which you can get from this curve also, but most important properties are the yield point, the ultimate point, the cracking point, for example, from where the first time this curve deviates from the linear line, and then the ductility of your cross section. You can have different kinds of curves for different values of axial load. As I have mentioned already, that the presence of axial load basically change the moment capacity, because the axial load and moment interacts in a cross section. So if you can give any number, for example here 100 kilonewton, and you click somewhere else, so you will see that the shape of that moment curvature relationship changes and the moment capacity also changes. The negative value basically will be the applied compression and the positive value will be applied tension. So you can have different kinds of curves for different values of axial load also. So if there is no axial load available, which means the pure beam case, beam doesn't have significant axial loads, so which means that now this curve corresponding to zero axial load shows you the moment capacity of the beam if this cross section is used to define a beam member. Similarly, if you use this cross section to define a column, that column will have a different capacity compared to this number depending upon what axial load that column have at that time. And also you can change the angle here. That angle corresponds to the orientation of the bending axis, so you can change that axis and your curve will be changed. For example, here you can see that the curve is changed. You can also click on this show tables and check the numerical values for this curve, and you can copy those values and you can paste them in Excel and plot it yourself. So here you can select all the rows and then you can click on this export to Microsoft Excel. So these tables will be exported to Microsoft Excel. So I click done here and I go to the last output, which is the interaction surface. So I click this interaction surface and I will get this form. Here you can see that this is the three-dimensional capacity surface of your cross section with P axis, M3 axis and an M2 axis. So you can go for different view options for this capacity surface. For example, this by default is the 3D view. You can go for this MM view, which is the top view basically, and then the PM3 view, the side view, and the other side view, which is the PM2 view. So you can also select a particular slice of this capacity surface and that slice will be shown here. You can check their numbers also. So these are the PM2 and M3 values for that particular slice. So I can toggle between these steps here at the bottom, and you can see that I am changing basically the slice which is taken from that three-dimensional surface. So these three values, these three columns will basically give you the coordinates for that particular slice. So I can go up to any orientation. You can see that as I am going to click this arrow sign here, so I am going to have different curves on that capacity surface. So I can have a maximum of, by default, 24 capacity curves, which are the slices of this capacity surface. So there are two display options available here. One is the show design code data, which means that you want to modify the axial flexural stress resultants by the code prescribed values, and you have to select the design code first also, which is same as the default code which you have used for the concrete design. So in this case it is ACI 318-14, but whatever code you select for your design purpose, the phi values and all the other factors will be coming from that particular code. So the other option is show fiber model data. So if you click on fiber model data, it will only show you the capacity surface which is originally calculated based on the fiber model equations, and these values will not be modified based on the code prescribed factors. So you can check this option here, which is the superimpose dashed design curve. So I check this option. So now I can visualize both of these options. So for example, if I check this option, show design code data, and I include the phi factor, which is the capacity reduction factor. So you can see here that the dashed line is basically the fiber curve and the solid line is the curve coming from building code, basically after modifying the values based on the building code factors. So you can see that the phi factor which is applied to the axial force have reduced significantly, but if you exclude the value of phi, you can see here that now the fiber model data and the design code data, they are very close. So also you can exclude phi factor and also you increase Fy. So in that case you can also see that now the value of code design data increase a bit in tension range, which means that the Fy has been increased based on the particular guidelines by this building code. So positive values are in compression by default and negative values are in tension. So if you increase Fy of your steel material or the amount of steel in your cross section, so you are basically increasing the capacity in tension side. But if you are increasing the concrete cross section size, then you will be increasing the cross section capacity in compression side. So this interaction surface is the basic tool which is used for the design of columns, and you can get the interaction surface for your own complex kind of cross section using this valuable tool called the section designer. So similar to M-Phi relationship, you can also copy these values. You can copy selected cells, for example, and you can paste them in Excel to plot for yourself also. You can also rotate this three-dimensional view both in plan as well as in elevation. For example, if I click on these values, so I am basically rotating it in the plan direction like this, horizontal direction, and if I toggle for these values, which is elevation, I will be basically rotating it in vertical direction. So you can have any possible view for this interaction surface, and also you can go to 3D to go for that default three-dimensional view. So the shape of this interaction surface also provides us a lot of useful information about the cross section and its behavior, and both of these outputs, which are the moment curvature relationship and the three-dimensional interaction surface, both of these outputs are very useful in the nonlinear modeling of cross sections when we are carrying out the nonlinear analysis or the performance assessment for our structure. So with this, I will end this session, and I hope that it was a useful session for you to understand this useful tool, Section Designer, for the analysis of cross sections. So I will see you in some next video. Till then, stay safe. Thank you.